welcome, and in this video I'm going to go do some linear regression. There's a certain project that I watched on YouTube, a practical guide to linear regression that I thought it was really good, and I wanted to try it out myself with a different data sets and slightly different circumstances. I'll link the video down in the description. It'll be similar in some aspects in terms of the code and more so the process and the approach, but there's differences, of course. Anyways, the code that I'm going to use here, or the data that I'm going to use here, is this data from UC Irvine Machine Learning Repository. It's an automobile data set, various features about things related to cars, and basically we're going to try to predict the price with some amount of variables. So we've got things like the horsepower, the bore. Honestly, I don't even know what a lot of these words mean. I don't know much about cars, but I thought this data set was pretty detailed, so that's why I wanted to use it. Anyways, this is the one that we're going to use. So we're going to get started here. Let's just, the zoom's a bit off. There we go. I'm going to start by importing various libraries that we're going to need. We're going to use the statsmodels.api linear regression model. So you'll see, but I'll just import a bunch of the libraries. We're going to need pandas and numpy, as usual with most machine learning tasks. We're going to use seaborn to plot. We are going to use, I'll also import matplotlib for plotting. Then stats models. That's going to be for linear regression. Then we're going to use various metrics from sklearn. They're going to be the mean squared error, but we're primarily going to be focusing on the mean absolute error. And R2, we won't need that one. And then this one here, probplot, it's another plotting tool. Import pylab. And then sklearn.preprocessing. We're going to do standard scalar and min-max scalar. And then we won't need those ones. That'll be all we need. Just so it looks a little bit better, we'll put this sklearns together. That'll be fine. Okay, well that's everything we need, and you'll probably need to install them with pip or with conda, however you like to install it, or at least some of them. These ones you probably won't, and same as these ones. Anyways, we're going to read in the data now. So we're going to do some pre-processing and exploratory data analysis. Just create a heading here. Pre-processing data analysis. So let's take a look at the data. We can kind of see what the variable tables are here, see what they represent. But just reading the data. So I've got it saved in a certain place. You'll see this. But it's a CSV file. And got it saved here. There we go. Oops. There we go. So if we take a look at the data set, we get something a little bit confusing. And that's because there's no section for the headers for the column names. So we're going to have to put in that by ourselves. I believe what they put here is just the first line as the columns, if there's nothing else there. Or maybe they put the average, because this one is definitely not the first one. Curious, maybe they do. We can try it out. 1, 3, 4, 5 dot. Can we just do mean? No, we can't do mean. Okay, so it's not numeric. Doesn't matter anyways. I could just convert it to the float and then can we do that? Oh, there's NaN values. Don't worry. I was going to see if if this value is the average of all these, but it doesn't really matter. That was just out of curiosity. Okay, so we're going to need to pre-process this so that we get, well, for one, we need to add the column names. That's probably the first step. Okay, so we're going to create a new data frame, and we're just going to create a copy of the original one, and that's just so that if we need the original one, we don't have to load it in again, because it could, I mean, with other data sets, it could take longer. With this one, it won't take that long. Excuse me. So, but just for completeness, we'll create a new data frame here, and we're going to set the columns now. Now I've got a list of the columns on notes here, which tells me what to use, but I mean, you could just go here, and it turns out they're back to forth, they're reversed. So you expect the first one to be the first column in the data frame, but price, that's the last column you can see here, because price would not be 3, 1, or 2. That doesn't make any sense. But if you go to the end, then this column here, this feature, it features values from -3 through to 3. And if we look at that first column here, which is just, right now it's just 3. So df3, if we look at the unique values, we see that those are what it is. And then if you look at the next one, that's the normalized losses, and so on. Right, so we can set the columns here, and I'm just gonna write it out here. I'll probably just edit this part out. So I've put all the column names here, and you see that you might notice that all of them are lowercase except for the target variable, which is price. That's just the way I like to do it, just to segregate the target variable with the other ones to the other ones. I don't think I've seen it. Maybe it is done like that, I'm not sure. Anyways, that's how I like to do it. Right, so if we run this and then look at info, we can take some more information about each of the columns. And what I've actually done is go through all of these variables and make sure that the unique values are what they say they are here. That's just good habits if you have a data set. I mean, if you're very trustworthy, you can just trust them, but sometimes you get different values for each of the variables that aren't shown here. Like, well, a common example is the NaN values where there's null, but there's other cases as well. Like I've seen data sets that have random letters or random variables there that aren't shown on the description here. So there's some variables here that are objects. They should be integers or floats. Like for example, horsepower, RPM, price. I mean, some of them they've shown as floats, which is good. So a good idea of what to do next since I don't know much about cars, is to go into ChatGPT and find out what these variables mean, what these features mean. You could just search them up on Google, but we've got very strong AI nowadays, so it's much easier to do this. And the prompt that I'm going to use, I'll just type it in and then edit this part out because it's a little bit long. Okay, so this is the prompt. With reference to automobiles, create a list where you define each of these, and each of these are the variables. These are just all the variables they used in the data set. If we run it, it gives us a list. Now, I don't know if this will be the exact same as the one that I've got copied in my notes, but I'm just going to copy the one that I have in my notes over. Should be pretty similar anyways. But yeah, it gives a description, and that's good enough for me because I just need a rough idea of what each of the features represent. If this was a more of a professional project, I would find out much more about each of the features. Perhaps even talking to someone that knows, actually definitely talking to someone that knows more about cars. So I'm going to ask them questions about each of them and how they, and then get an idea first of how might they change the price. So I'm going to guess based on what I think which of the features would have a big effect on the price and use those in a linear model. But if I was really doing this professionally, then I would research and talk to people who are more experienced about cars and find out, which ones I would think would have a big effect on price and how exactly I think that would have an effect on price, just so I have a hypothesis beforehand. Yeah, so it even says at the end, these terms are essential in assessing value in the market. Anyways, if I copy that in and convert it to raw, this was the prompt or the result that came up when I first used the prompt. If you like, you can go through it. Maybe you already know about cars, so you don't have to. But what I did when I first went through this project is read through this and get an idea of just what they represent. It's a good idea to know what the data that you're working with actually is. Okay. Okay, so now what we're going to do is understand the feature values. I explained this before, so I got a bit premature there, but now what we're going to do is look at each of the descriptions here, take a look at what values they show here, and then see if those values are inside the actual data set here, or if there's other values as well. So I'll just give you a few examples here, and then I'm not going to do all of them because we're going to have to go through all of the variables. But we'll start with symboling, which is the first one. And what I'm going to do is look at the unique values, and they are as they should be, from -3 to 3. There's no 3, in fact. So what was this value again? Symboling indicates the risk level associated with the automobile. It's used in insurance. And high numbers indicate higher risk. So there's no really high risk automobiles in this data set. That's what this one shows. But essentially we just go through each of them. And next one is normalized losses. Okay, so normalized losses should be continuous from 65 to 256. 65. Now this one is ordered badly, so we can go np.sort, numpy.sort, and this sorts it from smallest value to the largest value. But you'll see, and I remember this part here, you'll see that it sorts it weirdly. So it goes from 101 through to 256, and then 65 through to, well, question mark, but 98. We can see that this section here is ordered properly, and this section is ordered properly, but there's some reason why they're not sorted, and it's because the data type is an object, so they're not integers. If we convert it to integers here, .as type or float, I'm not sure if we'll be able to do this because there's the question mark value there. Yeah, I don't think we will. We'll do that later, that's fine. But we can see that the values range from 65, this is the smallest one, through to 256, which is as expected. But there's also a question mark here, and the sort is off. So we can just write a note here at the end, null value, and we can write, well, I've got on my notes bad sort, but we already know why that is, and it's because the data type is an object. We could write object there, but we'll just write it for completeness. But in a later stage, we're just going to go through all the objects and all the features anyways and convert them as appropriate. But we'll just write that object there. Object should be float or integer. Okay, well that's the second one. Go through just a third one, and then I'll copy the rest over. df. Next one is make. And you can go through all of these and check that they're the same ones here. I'll tell you right now that they are. But essentially that's what we're doing. We're looking at the unique values, and a lot of them don't have too many unique values, so it's not a crazy ordeal to look at all this. If they had thousands of unique values, that'd be different, but these ones don't have too many unique values. So it's manageable, definitely. But anyways, I'll edit this part out and I'll copy all the rest of the code, and then we'll go through that afterwards. Copy the code from my notes here. And you can see that I replace the null value just with a question mark here to represent where they have a null value, and then bad sort to represent, because I didn't figure it out actually when I first wrote this as to why it was sorting weirdly. So that's why I just wrote bad sort. But we know now why that's the case. So yeah, we remember that price was an object, and that's why it showed bad sort. That's why I sorted funny. Let's look at horsepower. Well, a lot of these examples are actually pretty much the same. I was just checking to make sure that the values here were consistent with the values here in the actual data set. And they were, so there wasn't any issue. There was just some question mark values, which I'm just going to change them to null values later on. Okay, so after going through each of the variables there, we are going to convert the null values, convert the question marks to the null values. Firstly, we're going to just find out how many null values there are, just so we can get an idea of how many values we're not going to have. What's happening here is null. Yes. So what I'm actually doing here is trying to find out if there's any actual null values prior to it. So we've got the question marks as the null values, but are there any proper null values prior that we're missing out? But that's fine. So we're going to convert all the question marks into null values now. We can just get an idea of how many question marks there actually are. And That's by doing, we can use the in function here. And we're just basically what this is asking is that the values of df, is it in this list? So if we put a 45 there, for example, then it would ask, is it a question mark or 45? But we've just got a question mark here. We have to put it in square brackets as a list, by the way. It won't work if we do it like that. But this is a good way to find out is, are any of those values question marks? So if we just return it like this, we're going to get a bunch of falses. There are trues somewhere, by the way, but you just can't see them here. But if we sum up all the values, we can see how many question marks there are. It's 4 in price, a lot of them in normalized losses. And normalized losses, what does that mean? That one means relative loss in value of a vehicle compared to other vehicles. I really don't understand that one too much. Loss in value of a vehicle compared to other vehicles. Relative loss. Well, if we use that as a feature, I don't think I actually use that as a feature in my analysis, but if we do, then I'll definitely look into that. But yeah, so normalized losses, there's a lot of them there, but we're not going to really drop that unless we use that as a feature. So if we dropped all the rows that contained the NaN values or the question mark values, that would be a lot of values to drop, because if we look from before, we can see that there's 204 entries. If we drop 40 of them, that's going to be a lot of entries dropped. But if we use normalized losses in the linear regression, then we're going to have to do that, because linear regression doesn't work with the null values. So unless we encode them differently by taking the average, but I wouldn't do that because it's a small data set. It's 204 entries. If you take the average of that, well, it's going to be even less if you take away the null values. So 164, if you take the average of that, that's not going to be very accurate. So we definitely wouldn't encode it that way. That is, we wouldn't change the question marks to the average. So we'd have to drop that row. And that's why I wouldn't use the normalized losses in the analysis. Okay, so we're going to replace the question marks with null values, and we just do df.replace, place the question mark with np.nan, which is the null values, and in place equals true, which just saves it as the original data frame, so we don't have to set it equal to the same data frame afterwards. Okay, so that's going to convert the question marks to the null values. Now we need to convert objects to the floats. So we can look at the original data frame here. We can see what objects here do we need to convert to floats. Which ones should be objects or strings, and which ones should be floats or integers. Normalized losses, since that is a value continuous from 65 to 256, that should be a integer or a float. The make, this one obviously should be a string. Fuel type, aspiration, number of doors, well, these two should be strings or objects. They can stay as that. Number of doors, that can be set as an integer. So we can do that. So we can just keep track of these. I'll just give you, so if we go through each of the features like that, we can get an idea of which ones we want to convert to integers and floats. And the way to do that is just as I've shown, you just go through each one, see what they represent, see what the values should be, and decide whether or not to, if they're going to be used in linear regression. we can encode some of the objects to, or the strings to some numerical value, and that way we can use that in a linear regression. But we can't use categorical variables in linear regression. So the make, if we leave it as this, we won't be able to use this in linear regression. If we somehow encode it to values, then we can. Objects that we are going to convert into floats. They're going to be normalized losses, bore, stroke, horsepower, the RPM, and price, of course. And do that on the next line here. So that's column there, all those columns. We're going to convert them to as type floats, like that. So we look at the gf.info now. You can see normalized losses as a float, bore is now a float, same as stroke, and so on. And then we are going to deal with the number of doors and the number of cylinders separately. So if you remember number of doors, if we look at the unique values, we can get 2, 4, and nan. And then if we look at number of cylinders, we get 4, 6, 5, 3, 12, 2, 8. So we're going to convert those to integer. We can't convert them to floats just like this or integers like this because, well, it wouldn't make sense because they're actually spelt out, the words. There is a library, I'm pretty sure, that deals with this and maps each of the worded numbers through to numerical numbers. But we can just create, because there's not many values here, so we can just create the dictionaries ourselves. And we can just go number of doors dict. There's multiple ways to do it. I'll show you 2 ways. So this is the first way, and this is fine for where there's not too many values or too many mappings. So we just do it like this, where we map the worded 2 through to the numerical 2 and the worded 4 to the numerical 4. And then what we can do is just do tf num of doors and then just map it like this. Like that. And that's just going to apply this dictionary to this column and save it in the original column. So this dictionary here, wherever it sees a 2 spelt out, it's going to convert to the integer 2. Wherever it sees a 4, it's going to convert it to an integer 4. And it's not going to do anything with the nan values, it's just going to leave them as is. Like that, there we go. So if we look at info now, we can see that number of doors is, well, it's a float. I don't know why it's done that, but we can convert it to an integer if we want, but there's no harm in leaving it as a float. But if we look at, I know why it's now a float. I'll tell you why. It's because there's a nan value. So nan values or null values can't be converted to, well, an integer. A feature, or there's a better way to say this. Features with of type integer, they can't have nan values. So if there's a feature and it has a nan value there, it's got to be numeric, then it has to be converted to a float. And I can show that this way. If we go number of doors as type int, we'll get an error, and the error is cannot convert NA or infinite values to integer. But float is fine. That's fine. There's no issue with that. But anyways, that's the first way of mapping those values. And the second way, this is a better way if we have a lot of values. Otherwise, it'll be a lot of lines that we use. Now, we could do it, we've got 4, 6, 5, 3, 12, 2, and 8. We could do it with each line. Go 4 to 4, 6 to 6, 5 to 5, so on. But I'll show you a different way to do it. Number of cylinders before. So these are going to be all the worded values, and these are going to be all the before values, right? They're going to be converted to something else, and these are just going to be 2, 3, 4, whatever, 5, 6. There's no 7, and then we skip a bunch as well, and 12. And then we have the same style of variable for after, and these are just going to be in the same order: 2, 3, 4, 5, 6, 8, 12. If we copy this here, number of doors dict, this is just going to be then zipping the two like this. Zipping the two, zipping number of cylinders before, which is this one, zipping it with after, which is basically going to combine the two elements by elements. So we have 2 mapped, or 2 zipped with 2, 3 zipped with 3, 4 zipped with 4, and so on. And then we just convert that to a dictionary. If we just leave it as a zip, I believe we just get a zip object. Oops. Yeah, we just get a zip object there. But converting it to a dictionary will show what it actually represents, which is that. So we could actually do this we could just do this manually, but this way is a neater way if you have many values to map. Okay, and then we just copy this and we do the same thing here, except with cylinders. Now the problem is if I run this again, it's going to give an issue with this because it's going to do it twice then, and it's not going to find any 2 or 4 values. So it's just going to give a bunch of null values for every... Well, I'll show you what happens actually. So if we run this and then look at df.info, you can see the number of doors has 0 non-null values now, so every value is now null. And the reason for that is we ran it once, which converted the 2's strings to the numbers, to the integers. But then we ran it again, but there were no strings now, so it just converted everything to a null. I believe that's what happened. That makes sense as to why. Because when I first saw this, I was confused. I thought there was a problem with my code, but I think it's just the way that these mapping functions work. But yeah, you can see that because we only ran this once, the number of cylinders, we can see now that it's an int, and well, the reason that it's an int is because there's no null values, so it converts it to an int. There you go. So we're going to just have to restart the kernel and run all this again so we get a proper result. There we go. We could have just run it from here, honestly. That's fine. Okay, so if we run it again, we get number of doors now only has 202 non-null, which is as it was before, and it's a float. And then we've also converted the number of cylinders to an integer. So I'm happy with that now. Now we can find out what to actually do with the null values. I mean, a spoiler is that I'm just going to take away the price null values, which have to be taken away. It's very rare, or there has to be very specific circumstances for you to encode the price null values to something else. And one of those circumstances is you need more data. This only has 205 instances, and I don't know where the 205th is, but over here we have 204 instances. That's fine. So that's not much data, so we can't really take the average of it, or I mean, it just wouldn't be right to encode the price to something else, because we're actually basing this linear regression model on trying to find out the price. So if we just guess the price, then that's just going to be that's not going to cause that. That's not going to make an accurate model. There's going to be a bias, and that bias is going to be based on what I think the price should be. And we don't want a bias. We want to minimize biases. So I'm going to take away all the price null values. So if we look at the null values again, if we just look at is null, we've got a bunch of trues and falses. So that's why we put the sum in the end. We can look at where the null values lie, and I'm just going to get rid of this one here. So we can see that there's some in normalized losses. So if we look at p dot and there we go. So we can look at the normalized losses. Is it in np.nan, which tells us which of the values are null, and then we just put that into the data frame to look at what are the rows where normalized losses is null. So this is a good habit to get into, especially if you have more professional data sets. And it's a good way to see what the actual null values, what sort of rows contain the null values. So because I don't know too much about cars, and I haven't researched too much about cars for this project, I can't really say much about this. But this is what you do in a typical situation. And you can do this for all of them. So you can see that there's for number of doors as well. So you just input number of doors. You can see where the number of doors is nan. And you can kind of ask yourself why those are the nan values, like why we don't have a value for that. And the other features of the same row can give you an idea of that sometimes. But what we are going to do is skip all the rest of them and just look at price, because that's the main one. We can there's not really much telling us, I don't think, as to why. I mean, we've got a bunch of column features here that aren't shown. We could look at those. That's fine. What I'm going to do is just drop all these. There's only 4. And we don't have too much data to start with, but there's only 4, so I'll drop these. And we just use df.dropNA. Axis is 0 tells us it's the row. If it was axis equals 1, that would be the column. And then we specify just the subset of the columns that we want to drop if they have NaN values. So if we didn't put this value here, it would drop all the null values, all the rows containing null values from all the columns, which would be a lot to drop, and it's unnecessary. So we just drop price and in place equals true to set it as the original data frame. Okay. So if we look at info now, we can see that there are now 200 entries. So price has, and you see for all of them, they've gone down from 204 through to 200. or they've gone down by 4 essentially, or most of them, at least, unless there was a overlap between the null values between multiple features. But yeah, we've lost 4 values. It's worth it to actually specify how many rows we've lost here. Lost 4 rows. It's just good habits to get into. Okay, so now what we're going to do is the last stage of the pre-processing. We are going to convert the object type features into integer values. We're going to encode them. And these are the ones that we might use in the linear regression. I wouldn't do this if I don't think I end up using these in the linear regression, but just to show you what I mean, we would use this if we plan to use this in linear regression, because like I said before, linear regression relies on numeric values. We're not going to be able to use string values for that. So if we want to use a variable or a feature that has these categorical string values, we need to convert them to numerical values first, encode them somehow. And if they have some sort of order to them, we can do that pretty easily. So if we can look at ChatGPT and ask ChatGPT if there's some sort of relationship with some of these variables to the price. So I forgot what exactly, I didn't write down the exact prompt that I used, but it could be something like order these variables, or these values, and then we put the values here based on their contribution to the price. So if we have the drive wheels, for example, all these values, four-wheel drive. So those are the values for drive wheels. If we look at drive wheels, we have these values here. All these values, based on their contributed price, they represent the drive wheels of automobiles. It's kind of a messy prompt, but I think it'll still, it still gives us a result. So it says that the front wheel drive are often least expensive, then followed by rear wheel drive, and the most expensive typically is four wheel drive. That's pretty much what you'd expect, or at least what I expected. So we've got an order here, and the way we could encode them is just by doing the map function as before, but we'll just do it inline. See what I mean? So we can look at aspiration. What was that? No, getting ahead of myself. Drive wheels. And we're going to set that to the same column, but we're going to apply the mapping to it. And the mapping is just dictionary, where rear wheel drive is 1, front wheel drive is 2, and four wheel drive is 3. There you go. So we're just mapping all the strings of rear wheel drive to 1, and then front wheel drive to 2, and then four wheel drive to 3. And that's just going to create some sort of order. And you can see that the order that I've used is where this one's the least expensive, then followed by middle expensive typically, and then the most expensive typically. Now there is a problem with this because I'm introducing a sort of bias. I'm expecting the order to be that way. I believe that if you're not completely sure that the order will be like this, then you shouldn't do this, because then it will introduce a order bias. because it could be wrong. It could be that it could be that the front wheel drive might be behind rear wheel drive for a lot of them, just because of the small sample size. But just to show you what I mean, I'll leave this in. And we don't use these variables anyways in the linear regression, so it doesn't matter. And then I'm going to do the same thing for the other ones. I'll edit this part out. Okay, so I've copied this in, and this was my original code, so it's got a note at the top here. And what I did originally is just go through each of the object variables to look at if I'm going to encode them. So make, I didn't care to encode, same as fuel type. Body style, I didn't care to encode. And each have the reasons. For example, make, there's just too many factors that are involved in. I mean, obviously, some styles of cars, some makes of cars will be more expensive than others just because of the brand. But I kind of stuck this just to the ones that are a little bit more simpler. So I left it with engine type. I converted engine type to numerical values based on the same ChatGPT prompt, but I used it for engine type instead. Did it for drive wheels and then aspiration. This is a new day for me, but this will just continue on the same video for you. So I've got to read in everything again. And I'm going to continue on with analyzing the features now. And what I mean by that is we're going to create some diagrams where we can see how the features interact with one another. And the purpose of that is to find out which features to actually use in the linear regression model. We're also going to see if there's any correlation between some of the features. You can do this intuitively by saying, well, for example, curb weight. So the weight of the vehicle will be correlated with the length, width, and height. Because obviously there's different materials weigh differently, but still, if you have something that weighs a lot, probably going to need to be at least tall, wide, or long. And if something is longer, it's got to be wider, otherwise it's going to look quite silly. And the height is correlated as well. And then maybe the highway MPG, and then the city one might be correlated. Like I said, I don't know too much about these words, but what we can do is also look at the pair plot between specific features and see if as one increases, another one might increase, and if it's correlated in a way where we can't really. So I'm going to explain this. So if it's correlated in such a way so that, like for example that I gave before, a vehicle that weighs a lot, it's got to either be long, wide, or tall generally. So we can't really, if we fit a linear model to the curb weight as the feature, then it wouldn't really make sense to put another feature as width or height, because curb weight is already correlated with width and height, so it's just causing too much complexity, decreasing the degrees of freedom as well. And generally you want more degrees of freedom, because that way you have more telling model, really. So, but we'll get to that later when we look at the statistical analyses. So we're going to do a pair plot. I've already got these saved, but I'll write down the code. Anyway, so we're going to go pair plot full. Oh. So this is a Seaborn feature, a Seaborn tool that creates various graphs of the numerical features and it links them together so that you can see the correlation between features, and you can also see how much a specific feature appears because it will create some histograms as well. See what I mean? But this is the code for it. So I'm storing that in a variable, and now we can plot it just in the Jupyter notebook here. But it's much easier to zoom in and zoom out because we're going to have a lot of features in this. So I'm going to save Fig, and then what do we have? So I'll just write this out here. Users. There we go. So I'm not going to run this because it's just going to take a long time. I've already got saved anyways. So what comes up is this, and you can see what I mean with the zoom being useful. So each of these graphs represents the relationship between one of the variables to another, and it's only the numerical variables, because there's no way to include the categorical variables unless you can code them somehow. But for example, you have price versus normalized losses. So there's not much of a relationship here with normalized losses and price, but something like length and price, you can see that it's kind of exponential actually. As length increases, the price of the vehicle generally jumps. And curb weight, that's more linear. Curb weight and highway MPG, this is, where did we have it? Oops. I went to the next one. All right, I've got it back here. So what was it? Curb weight. So you can see it's hard to navigate through all this, but curb weight and highway MPG. So as the curb weight increases, less the vehicle can travel less amount of distance on a tank of gas, and that makes sense. You know, as the bigger the vehicle is, the more taxing it is to carry from one place to another. So generally that's the case. It's inversely related. And then on the diagonal you can see we have histograms, and these are just because the variable on the x and y would be the same, so it'd just be a scatter plot of, I don't know, city MPG versus city MPG, or horsepower versus horsepower, and that would just be a straight line. So instead we have histograms here, so it tells us where the values are generally distributed. So for example, price, which is the one at the end, most vehicles are in this region here. So what's that, around 50,000 through to 150,000, and then some are around 200,000. That's not right. 5,000 through to 15,000. I was going to say that's some expensive vehicles if most of them are situated around that. And then 20,000, some of them, and then you got some outliers later on for 30,000 to 40,000. Now it's interesting that we have the prices capped at like 50,000. Maybe this was I think this one might have been an older data set. I'm not sure. Because I mean, some vehicles are even more expensive than that nowadays. But I guess this is only 200 samples or something, so it probably won't show those ones because they're not common. And then what's this here? For example, if we go down here, number of cylinders. So this wasn't a continuous variable, this was a discrete variable. You can see that most of them are, I don't know what this value is, but we can find out if we want to, but most of them are this value anyways. But yeah, that's what the pair plot would come out with. Now, if we go to the next line, I'm just going to comment this out so I don't accidentally run it because it'll take a long time. And then another one that we want to, I just want to note that with this pair plot, it's also a good idea to look at the outliers, which features have outliers, especially the target variable, which is price, because we might need to remove the outliers. So I've noted down here that there's some outliers with the price and compression ratio, engine size, and where you'd look at for that is the diagonal, because diagonal has the histogram, and that's where you can see the outliers for a particular variable. Okay, and now we're going to look at pair plot price. I'm just going to capitalize this because that's the way I do it. And we'll create another pair plot, but this time we're going to do price versus all of it. So we're just going to have a single row, and it's going to contain price versus all the variables. And this is because this is what I use to choose which features I want to include in linear regression. Because if we, we can use the pair plot from before to do this, but it's just a bit of a hassle because we need to zoom out and see what variable is which, engine type, and then go back in here, and it's just, there's a lot of a lot of stuff going on. So really what I'm trying to look at is just this final row here, which is price on the y-axis here, price versus all the other features, and that way we can get an idea of which features will change price, and we can try to fit a linear model. Like for example, I can see here that engine size is pretty linearly related to price, so I'm going to use engine size as one of the features for the linear model. But we're just going to get that row, and the way we do that is by specifying the data frame here, and then we're going to specify x vars and y vars. Now y vars, that's just price, because that's just the only variable we want on the y-axis. And then x vars, we want to go through all the features in the data frame, which is, it's got to be a list, so we can just write list there. It's got to be a list of the features, but we're not going to actually, I'm going to change what I said. We're not going to take all the features, we're just going to take the integers and the floats. And the way we do that is by writing df.select dtypes. So we're going to select the rows, or we're going to select the columns that have the particular d types of, and here they are, int 64 and float 64. So that's going to select all the part of the data frame, the parts of the data frame that only have integers and floats. So it's just going to select that subset of the data frame, but we're going to need the columns from it. So that's why we write dot columns here, except over here, dot columns. Yeah, and then we just convert it to a list. So if I go up here and I write df.select dtypes, you see it returns a data frame, and it's just going to be all the integer and float data types, and those are the only ones in 64 and float 64, because if we look at info, there's no other ones. There's either object, int, or float, and all the objects we're not going to bother. We've already encoded the objects that we want to encode, like for example, I think engine or number of cylinders, that used to be an object, but we converted it to an int. So you can see we have float 64, int 64, and none others. So that's why we're only including float 64, int 64 here. And then dot columns will just take the columns of those. Right, so we want all the features of the data frame that are ints and floats, and all we want for the y variables is price. And then we just save the figures again. And we'll call this pair plot price. That. So if I run this, it won't take too long, but I won't run it because I've already got it saved. So I called it auto price before, that's fine. So with this entire row, it's all just going to be price in the vertical, but we can see this is a lot simpler to visualize and scroll through. But for example, symboling, there's no real relationship, it looks like here, same as normalized losses. It's just kind of all over the place. Aspiration, number of doors, drive wheels. Maybe drive wheels is slightly negatively correlated linearly, but it's very, I mean, the bottom portions of each of the vertical lines here, they're not, hang on, they're about the same for all of the number of drive wheels. So what I'm saying is that if this bottom portion here of 1.0 was removed and some of the bottom portion of 2.0 was removed, there'd be a stronger negative relationship. But wheelbase, that's more correlated linearly, same as length, width, height not so much, it looks like. Curb weight, yes. Engine type, no. Number of cylinders, yes. Engine size, yes. Bore, not really. Kind of, a little bit. Stroke, very... I mean, this is a really crude way of finding out, because there's the specific statistical techniques like the p-value, which we'll look at later on, that we can see if a feature is correlated or is likely to be correlated. But this is a good way to do it, just to get an idea of what to feed into the model. So horsepower is another one, and then both of the city and highway MPGs, they're negatively linearly correlated, or more exponential, but we're going to fit a linear model. And then we have price versus price in the end. Okay, so we've got that, and then we're going to look at are any of them correlated with one another? So they are. A lot of them will be. And what I've got written down here is I've just written down the features that we could consider. And these are the ones that seem to have some relationship with price. Engine size, horsepower. And the reason I've written or is because there is some sort of relationship between the two. So we probably won't need to do both city and highway MPG, and we probably won't need to do both length and width and curb weight. Just one of them. And that's for the reason I explained before, that they're correlated with one another. Well, I'm just guessing that they are at this point. But we can actually have a look at their individual graphs and find out if there's any correlation with one another. And this isn't a final way to... This isn't a what's the word? Sufficient way to determine if there is this sort of correlation, because they could just be correlated with one another in a... but they could be independent still. But that's probably what I should have said before, that length and width are correlated with one another, but they're also dependent in a way. So length does affect width just by its very nature. You know, if you have something that's long, generally it's going to be wide as well, if it's a vehicle anyways. And then same as city and highway MPG, they're dependent on one another. There's no relationship with them in an independent way. But like, for example, the price, the target variable, it's not necessarily like... I'm sure there's a word to explain this, but it isn't dependent on engine size by its very nature. There's other things that affect the price, but engine size, for example, will affect the price just indirectly. If anyone knows the term for this that I'm trying to look at, then let me know. But so maybe I won't write are they correlate with one another, but what we're going to do here is just look at the pair plots between the two, between all of the features that we have here. So we have wheelbase. So these are the variables that we're going to use here. Length, width, curb weight, cylinders. Really, I'm just writing down all the variables that I've written above. in the comments. There we go. Okay, so that's what we're going to do for the pair plot, and then we just save fig like before. Except this is going to be pair plot feature core. I'm going to call this alter feature core. There we go. And if we run this, we get this one here. So it's a little bit smaller. Wait, no, we get this one here. So it's a little bit smaller than the full one because we're only taking the features that we're probably going to be using. But, you know, like city MPG and highway MPG, you can see that they're almost perfectly linearly correlated. And they are dependent on one another in a way that is in a way where we're not going to probably benefit from using both of them. You know, so they're pretty strongly linear correlated. So if we use city MPG and then we introduce highway MPG, it's just going to be a greater complexity for not much benefit. At least I'm guessing based on these graphs here. But then something like, I don't know, wheelbase and city MPG, there's less of a correlation there, so we could potentially use both of those. Same with some of these ones here. So even these ones where they're not really strongly linear correlated, like length and wheelbase, kind of. I mean, that's more exponential, so maybe it would benefit from using both of those features. Because if it's exponential, then the linear model wouldn't take that into account, right? So we could potentially use both of those. Same as these ones where there's kind of like a curve to them, but they all are pretty well correlated with one another, it seems like. Maybe not this one so much. Watch this: number of cylinders and curb weight. I mean, you can kind of like rationalize that if something has more cylinders, maybe it's going to be bigger, or at least the bigger ones will have generally more cylinders. And that's kind of what it shows here. So the ones that have the most number of cylinders, which is 12, they're the biggest ones. Okay, well, we've got that. And that's the feature analysis there. So we're going to get over to the linear regression model now. Okay, so let me write the title here, which is stats. Oh. So that's the linear regression model we're going to use, and it's from the stats API, stats models library here from above. Where is it? There we go. Import stats models API as SM. Okay. Firstly, we're going to create a copy of the data frame just so that we can reset it if we need it. And we're going to create a deep copy. It's probably not necessary, but just for completeness. It's not really a huge data frame, so I'm not really, I mean, it takes more memory to do this code rather than just a shallow copy, but it's not really a big data frame, so it doesn't matter too much. Okay, so we're going to do various feature, or we're going to do outlier analysis later on. I'm just thinking out loud now. Okay, we're going to just make the model first. So the model is just made by using the stats model, and this was the alias that I used for it. And it's .ols, and then we fit it. So I've got my notes next to me, and I realized I missed something. So we're going to have to choose the features first, but This is going to be the format of the model anyways. And then linear model, that's model.fit. You don't have to call it linear model, that's just what I called it. I'm going to look at the summary as well. But you can see that with this format, we're going to need the Y, which is the target, and then the X, which is the features. So we're going to create those now. So we can call this choosing features here. And let's just stick to engine size. Just for the first one, if you remember, I'll show you anyways. Engine size is linearly correlated with price. So we can see that there's some relationship just visually, but we'll find out if it's if the summary shows that as well. So I'm going to create a data frame just called XY, which is going to contain, there's a reason why I'm doing it like this, by the way, and it'll be apparent later on. But we're going to create a copy of the original data frame, and it's just going to contain the target variables and then the not target variables, the features and then the target variable. And in this case, the feature is only engine size. Okay, and then we go drop NA because we're going to drop all the null values because we need to drop them, otherwise they won't. Otherwise, the model won't run. So stats models API assumes that there's not going to be any null values, so we need to deal with those. So if there's any null values in any of the features, now if you remember, we've already dropped the null values for the price, so that's not going to be an issue. But I mean, it is worth it to see beforehand if there's any null values. But if we go engine size, there are no null values, so there won't be any dropping for this one. So we're going to go axis equals 0, which is we're going to drop the rows, and then we're going to go in place equals true. And that's the reason why I created first this X and Y df with all the features and all the and the target variable, because if we want to drop NA, we want to drop rows across the target variable as well. Otherwise, the dimensions of X and Y won't match. Okay, so X is just going to be the target variable, so that's just going to be engine size. And then Y is just going to be price. There we go, so we've got X and Y. If we run this, we've got an error. Engine size is not indexed because it's meant to be like this. There we go. So if you look at the result, I mean, X is just the engine size there, and then Y is series this time, but it's price. And it's a series because we've got the one pair of square brackets here, and then engine size, even though it's one variable, it's a data frame because we've got the two there. So interestingly, if we look at x.columns, oh, I thought it was going to be a multi-index, but it's not. That's all right. So these are the regression results. The main sections we're going to look at is the R squared value, which you want as high as possible. It's going to be a value from 0 to 1, 1 being the best, but that's really unlikely to happen. That's only if the linear regression model fits the data points exactly, which is if it's a straight line. And then we're going to look at this value here. The closer this is to 0, the better. If it's, I still need to learn about what a lot of these values mean, but the basic principle is that if this is less than 0.05, then we're willing to accept that this variable is going to be useful in determining the price. If it's greater than 0.05, then it could just be a coincidence that this affects the outcome, and we would essentially reject that this variable would be a good determining factor in the price. But because it's 0, that's really good, so we can say that this variable is useful. So essentially that's the outcome of the model. So we've got a model here that we can work with, and we could just leave it at that, but there's various things that we could do. For example, we could look at the outliers, and we're going to do that up here. So if we want to look at the outliers and conduct an analysis of them, we can create a box plot with SNS, Seaborn. If we just plot this, just put a title as well. There we go. So this box plot tells us the distribution of price. 25% of the values are less than this bottom part of the box here. 50% are less than this line throughout the center of the box. Then 75%. Then we have the minimum and maximum, or minimum and maximum values, which is this maximum is this point up here, and then the minimum is just down here, this bottom line. And anything above the plot, any of these circles here, they're counted as outliers. So you can see we've got quite a bit of outliers, and if we look at, well, if you remember from the histogram from before, when we looked at the price histogram, we saw that most of the prices were at the beginning of the histogram, and then it leaned to the right, so it's skewed to the right. And these outliers would be all those points there. So we can actually just remove them, and then we might be able to get a better result with the model. So we can find the quartiles. So quartile 1 is this one here, the 25% value, and quartile 3 is the 75% value. And we get df model, and the way we get these quartiles is we use the quantile function, and then we take the 0.25 for that one. And then 0.75 for the third one, and then we're going to take the interquartile range, which is basically just the difference between the two. And the reason that we're doing this is because the way to find the outliers is by taking all the values that are greater than quartile 3 plus 1.5 times the interquartile range. So it looks like this, quartile 3 plus 1.5 times. So any values that are greater than this are the outliers up here. And then any values that are going to be less than quartile 1 minus 1.5 times its quartile range are going to be outliers at the bottom. In this case, there's no outliers at the bottom, but for completeness, we'll include this in the expression as well. So if we get into quartile range, it's going to look like that. And then to get the outliers, we just use that expression from before. So it's going to be everything in df model such that we're going to do this. It's going to look like that. So in this first one, we're going to take all the outliers at the top, which is going to be all the prices that are greater than quartile 3 plus 1.5 times the interquartile range. And then this bar means or, so or all the prices that are less than Q1 minus 1.5 times IQR. Yeah, so that's going to give us all the outliers, and if we just print print that out there. Oh, we need to define DF model. There we go. Those are all the outliers. You can see that well, if we look at price values, they're all quite large compared to the other values at least. And there are, what's that, 9, 12, 14 of them. So it's worth noting how many outliers there are. 14 price outliers. And we can actually remove the outliers by just writing df model.drop and then all the outliers but the indices of them, because we need to pass in the indices. So if we drop the indices, it'll drop 14, 15, 16, 46 and so on. So that's what we can run to drop the outliers, and then we can do this again. And you can see that the R-squared has changed, it's increased. I believe it's increased. Run it again to find out. So that's it. This is 0.923. Yeah, it has increased. And that makes sense, because if you remove the outliers, then it's more likely that the model will fit the average values a lot better. So before we work with some other things, we're going to work with transformation and standardization as well to try to improve the model. We're also going to add a constant later on, but we're just going to plot the results. I'll copy the code over and I'll explain all the code for it. Okay, so this is the code I'm going to use to plot this. There's also a QQ plot over here, which I'll explain afterwards. But over here we've got, well, first it's worth to say that we can predict based on the linear model. So if we just write linear model.predict, and remember the linear model is just this one here, then we can get a list of predictions. That did work good. If I show you what the predictions are, it's just a series, and these are just the predictions for the price based on each engine size. So these aren't the true values, but we can get the residuals by doing y minus predictions, where y is the true values. So if we subtract predictions away from that, we get the difference between true values and the predictions. And these values are going to be less drastic. I mean, we've got quite a big difference for 203, which is $7,000. But some of them are negative, obviously, because some of them predict higher than they actually are. And then if they're positive, then they're going to predict lower than they actually are. But if we take the absolute value of them, we can get the absolute residuals. So 246 will be a positive now instead of a negative. And that's going to be useful as well. We can get an idea of just the absolute values of the errors. And then this is the mean absolute error. This is a value, and it's going to be the average of the errors. 3,801. I'm not actually sure actually how it's calculated. It might just be an average of all of them, but well, that's doesn't matter for now. We just get the average mean absolute error, which is another statistics that we can use to determine how well the model fits. So with this case, if we remove the outliers, it was $3,801. But if we reset this and we don't remove the outliers, then the mean absolute error will be, maybe that's what I did before. It's the same, but that's a bit strange. Oh, okay, right. So if we do remove the outliers, then it's 2,835. But the one I had before, I didn't remove the outliers. So by removing the outliers, we get a lower error, which is good. But of course, we remove the outliers, so the model is trained on less data, and also it's less accurate really in the real world, because there are going to be a lot of values that are quite high for the prices. Because remember, the data set that we have here is quite small, so outliers here for this data set might not be outliers for the population data set, and I doubt it would be anyways, because this is just a small sample. So got to keep in mind that the outliers of a small sample aren't always outliers of the true population. So this first plot here, we're gonna plot, what do we have? We have Y, which is the true values versus predictions. So how well did the price get predicted? And that's this plot here. So the blue values are the predictions. So we have the true price down here, and we have the predicted price here. This green line is a hypothetical perfect prediction for each of the data sets. So that would be where the true price is equal to the predicted price. So that's just going to be a straight line. And that's this part here. So this is the green one here, which is just Y versus Y. So that's in a scenario where the model predicted it perfectly. So essentially, the more these points here, these blue points, are away from this green line, the worse the model did. But again, the model is, it's very unlikely to be close to it, or closer than, some amount. It's never really going to be perfect unless it's a perfect linear relationship. So then the second histogram here on the right, that's going to be a histogram of absolute residuals. So it's basically telling us what is the distribution of errors or of residuals. We're only taking the absolute values of these, so we're not going to look at the negatives. And then I've also plotted a line which is just the mean absolute error, and it tells us where the error is. And you can see it's roughly actually in the center of all these residuals. So you can see mostly the error is between 2,000 and 4,000, or 2,000 and 3,000. But then even it's skewed a little bit to the left over here. So you can see there are, and that's what you really want to see. You want to see most of the errors quite low, and then a few of the errors maybe higher. Like you can see the highest error is around 10,000, or around 10,500, which is quite large actually, considering that some of these prices aren't too high. I mean, we've got prices up to only about 30,000. So 10,000 is a big chunk of that. And you can see that that's actually probably the difference there that it's showing. So you can have the true price here of, let's say, about 30,000, and then predicted price of 17,500. So that is about 10,000 difference. So that's what this one would represent, because this is furthest away from the hypothetical perfect prediction, which is the green line, this final point here. And then the third histogram, which is the distribution of residuals with 25 bins. So these are just the residuals, the non-absolute values. So you can see we have negative values as well. The reason I've plotted this is because for linear regression to work properly, or to hold, we need to have a normal distribution of residuals. And you can see this one is not a normal distribution. Another factor that we need to consider is, are the residuals independent and was identically distributed? So then what we would see here, if they were, would be random points kind of all scattered around the area. So on the x-axis we have the data point here. I'll show you here. So on the x-axis we have the data point, which is going to be the length of residuals, which is what we're plotting, and then the range of that. So that's going to take us from 0 through to the length of residuals minus 1. And then we're just plotting the residuals. So if this was perfect, we would get kind of a random layout here, but we can see that a lot of the there is a sort of pattern here. So with with the data points, they go up high here, and the residuals are quite high, and then they go low, and then they go high again, and then they go low. So there is a pattern here, which tells us that the residuals are not really identically and independently distributed. There is a pattern with them. So what this is telling us actually is that linear model might not be the best solution for this, for at least this specific model. Maybe we can change it up a little bit to get a better outcome. So that's these 2 points here. So again, this is the distribution of residuals, and we're looking to see if it's normally distributed. It's not though. And with this second one here, this is just a plot of the residuals one by one, and we can see there is a pattern with them, but it shouldn't be. It should be more random. So in a perfect world, we'd go to well, first we'll play around with the model to see if we can get a more normal distribution or a more random result here. But if that doesn't work, then in a perfect world, we'd go to a different type of model. Maybe not a linear model, but maybe a logarithmic one or some other kind of regression. And then the QQ plot down here. So this tells us how normal our data is. This red line would be a perfect normal distribution. And the way it works is that the red line is plotted such that it would be a normal distribution. So we have the theoretical quantiles, which is the quantile of the normal distribution, and then the value that it would represent. So if the data was a normal distribution, then it would lie exactly on this red line. But you can see that it doesn't really. I mean, it's pretty rare to get actually something that's close to a red line, to the red line, but even this is quite off. You can see that a lot of the points are skewed quite negative here, or above the true value. So there's more values skewed to the left, and then there's more values skewed to the right, it looks like, because they're above the red line, and then there's less in the center. So what I'm seeing from this is that the true distribution is sort of more spaced out rather than a bell-shaped curve. There's more values to the sides, to each of the I'm missing the word here, but to the sides and to the left and the right, and then there's less values in the center. Okay, so that's what we're going to look at to determine if our model is going to work well. But we're going to try to fix this this issue with the normal distribution. So to make it more normal, we can actually transform the data, and we can do a square root transformation or a logarithmic transformation. And this sometimes works to fix that issue. So if we go up here, and just before the model, we can write np.log. It's that simple. That's all we're going to do to transform the data, and we can just write here, just so we know we're doing transformation. We can do a square root transformation as well afterwards. So yeah, we can do that, and we're going to reset this, do the model again, and print the result. So you can see that this doesn't work well at all, does it? It changes the model, definitely, but it doesn't change it in the way that we would hope to change it. So all I did here was just all the X values. Or do we need to do it to the Y result as well? Might have to do it to Y as well. I'm going to try that. No, because the mean absolute error is 0, and that doesn't make any sense. So it looks like we would do just the X value there. Let's reset this. Yeah, so that one didn't work too well, it looks like. So the predictions are quite off. They're actually quite consistent. Predicted price is the same for a lot of these. But let's try the square root transformation. Now we wouldn't do it on the target variable, the price, because that would change the whole point of the model. The features we can work with, the features we can change around. So that's why we can perform the transformation on the on the engine size, but not on the price. But yeah, for the square roots, we get a similar result. So this one didn't work out too well. Sometimes it does, but in this case, we still don't have a normal distribution. We could do a different sort of transformation, well, a standardization, which is going to be either a min-max scalar or a standard scalar. So I'm just going to do both. So we can create the scalars for standard scalar and min-max scalar. In fact, min-max scalar might be better for this situation because I'm pretty sure the standard scalar assumes a normal distribution. So then we apply this. Let's do min-max scalar first. Fit transform. And then convert it back into a data frame. With the same indices. Let's try that one. So we're going to do a min-max scalar. This one did a lot better. So I believe this is actually less with the scalar. And yeah, you can see it's much more normally distributed now. The QQ plot is a lot closer to the line. So this actually would be a good normal distribution. I would consider this good. The residual values look to be a little bit more random. They still have a little bit of a pattern to them. It goes high, then lower, then high, then lower, then high and lower. But it's less of a pattern now than before because each of these high points are different, and then the low points seem to be different as well. It's probably fine in this situation because it would be unlikely to get it perfect or even close to perfect. So I would be happy with this actually to use the linear model, especially because the QQ plot, that's very close. You often get actually with the QQ plot, the end values are not on the line. They're usually either higher or lower. So that's actually quite common. You get with the probability plot. And then we can also, curious what happens if we put the standard scalar instead. Let's see if that does anything good. So the standard scalar, that did not work well. I mean, it's kind of more normally distributed now, but the predictions are well off. They're below. The R squared value is very low, 0.089. So we're going to switch to min-max scalar. And you can see the R squared value is high now in this case. And we've got values closer to the perfect predictions. We've got a normal distribution, more of a random residual value, and then the probability plots is much more consistent to a normal distribution. Okay. So we're happy with that, but now what we can actually do is play around with, there's one more thing we can add. We can add a constant into the regression. So we can just do that prior to the model here, and a constant just adds another variable that's going to be, well, a constant. And we do this after the scaling because the constant will, I believe the constant is actually determined on factors related to the model or the data. So if we scale the constant, then that's messing around with the reasoning as to why the constant is the way it is. So whatever it is, we'll just leave it as it's chosen, and that's after the transformation. So if we run this, well, it's less normally distributed now, and the pattern is more pattern-like, or it's less random, I should say. Mean absolute error, I think that actually went lower. I'm not sure. But in any case, we've got less of a normal distribution now. So even if the mean absolute error did get lower, then we would still not choose this because it makes the linear model, the assumptions that underlie the linear model, it doesn't make them hold anymore. We don't have the normal distribution. So, I mean, the R-squared value is lower in this case anyways. So we're not going to run that. But what we are going to do is add some more features. So we've done engine size. Let's add horsepower now. And I've got the graph here from before that we created. So all the values versus price. So we can see horsepower is linearly correlated with price. Price is on the y-axis here. And if you look at the correlation between horsepower and engine size, which is over here, horsepower and engine size. So you can see they are related. So we can actually find out if, well, it will tell us if horsepower is going to be a useful variable. I'm not quite sure if we're going to be able to determine if there's a correlation between the two with the statistical results. Like, I don't know if the statistics will tell us. But then again, I haven't looked too much into the statistics there. That's something that I've got to look into more. But maybe we'll see what happens, but maybe we'll do something else afterwards instead. Like maybe one of these. Well, what do we have? We have engine size. So we want to do engine size and something else. So maybe engine size and wheelbase. That one's less of linear distribution between the two. And then engine size and maybe one of the MPGs here, city or highway. Because if we get a correlation between the two, you got a linear model and you're adding in another variable that can just be worked out with the original feature. So it's kind of redundant. Anyways, we'll go horsepower here. And then horsepower here. I believe that's actually all we need to change. Yeah. So we'll run this again. We'll keep the... Oh. And if you remember over here, we've dropped all the null values. So I believe there actually are null values for the horsepower. If we go df horsepower, does that one work? What is it? Is nan? Is null? There we go. Wait, no, it's not. There we go. So if we take all the null values, there's two of them. So it's going to remove some rows, but it's going to remove the rows from price as well. So we're not going to get an index. We're not going to get an issue with matching indices. But let's run this again. Okay, so let's look at the values here. So we can get, well, we got 0.926, and then it's telling us that horsepower is a good indicator of the price. This doesn't tell us anything about the correlation between the two. It just tells us if individually. I don't think it tells us anything about the correlation, but I'm pretty sure it's just individually if they're. Well, in this case, if you don't know too much about this, don't worry. I don't either actually. I need to look into this more, but it's related to a concept called the null hypothesis, and it's basically we're assuming that in this case, horsepower and engine size is not a good determining factor of the price. So we're assuming that it's kind of random. that the linear relationship is random. That's the null hypothesis. And we're essentially saying what is the likelihood that we can reject the null hypothesis, which is that. So here, because it's 0, it's very unlikely that if we rejected the null hypothesis, we would get it wrong. And what that means is that it's very unlikely that if we rejected the fact that horsepower and engine size is not a good determining factor of price, we would be wrong. Because it's basically, that's what the 0% mean. If this was like 5% or something, 0.05, then if we're going to use horsepower as a good factor in determining price, then we would be 5%. There'd be a 5% chance that we'd be wrong and that we shouldn't have used it because it's random. And horsepower is not a good indicator of price. If that didn't make any sense, well, you can watch another video on it. There's plenty of good videos on the null hypothesis just in general. But if that didn't make sense, don't worry. I'm not going to go into it in detail in this video anyways. But essentially this is 0, so that's good. We're going to use these values here to determine the price, but they are correlated if you remember. So we're not really getting too much of a better result with this. If you remember, well, I don't remember what it was exactly, but the mean absolute error is very close to here. The R-squared value is close to that as well. I think it actually might have been the same, and the QQ plot looks the same or actually even worse than before. So in this case, I mean, you could like go through all the steps. So with these two features, you could keep the outliers in, you could add the constant, you could do every sort of combination between that and the standard scale, the min-max scale and all that. But that just made the video way too long. So I'm just going to stick to this. So we're going to remove the horsepower. We'll keep an engine size. And we will put in, what do we want? Wheelbase, right? Yeah, wheelbase and engine size. They're not too correlated there. So wheelbase. Like that. So essentially the rest of the modeling process is just testing out the variables like this. So this one takes the mean absolute error much down to 2,100. So this I would keep, and you see the residuals are much less now. So they're almost 0 actually, between 0 and 1,000. All the residual values plot is random enough. It's still normally distributed, which is a big factor. And the probability plot is, well, if you remember from before, this lower portion here, this was below the theoretical red line. And now it's pretty much on the red line, so especially this lowest point here. So this is good. This tells us that it's useful to keep wheelbase in. And R-squared value is higher at 0.943. This value is 0%, so it's telling us that wheelbase is a good indicator of price, probably. Well, it's basically saying that it's a 100% chance that it is, or almost 100%, because there's going to be some decimal points there. But anyways, we could also do a city MPG, this value here, because this is correlated, but this is exponentially correlated. Or is it logarithmic? I don't know, but in any case, it's not linearly related. And we've got wheelbase now, so if we look at wheelbase versus city MPG, that's not too correlated either. It's kind of linearly correlated, but it's like a triangle shape. It's all over the place. So since they're not really correlated with one another, we could add in city MPG like that. We don't need to add in highway MPG because that's related to city. Okay. Oh, so that's about the same as before. R squared value, I think that's a little bit lower. Okay, so here it's saying that it's not a good indicator. So this is a high value. This is 0.6, and because it's basically saying that if we say that city MPG is a good indicator of price, we are likely to be 46% wrong, roughly like that, or is it? Well, actually, no, it's 64.6% wrong, I think. Actually, don't quote me on that. I could be wrong with that. But in any case, it's high numbers, so we're using a 5% value. That's typically the value that we apply to this situation. So if this is less than 0.05, then we're going to take in the variable. But in this case, it's 0.646, so we're not going to use that. Even if it looks like the probability plot is great and everything, it's not a good indicator. And I wonder if that's because the price is. Yeah, so you can see it's likely because the city MPG and the price are not linearly related in this plot here. So if we use peak RPM, that's probably unlikely to be a good value either, because that's all over the place. Engine size, that was good. Curb weight, that's kind of exponential as well, so that probably won't be good either. I'll use wheelbase, and that said it was good. But that's because most of the points are centered around this portion here, and that portion by itself is quite linear, so maybe that's why I showed it was good. But it looks like we've kind of reached the end of all the features that are obviously linearly distributed. In this situation, what I do is, if I don't want to, so I'll just go back to the model that we had before. So if I still wanted to mess around with models and find a better one, which I would if this was professional, then I would go through some of the other features just to make sure that they can't be used. Maybe they can be. I also remove portions of the outliers rather than removing all of them at once and seeing how that affects the outcome. I'd consider the outliers separately, maybe by applying a linear model to them separately or some other model, because outliers can be quite drastically different than the normal result. In this case, they aren't too drastic, but in other situations they would. I would see how these affect it, the standardization, the transformation, and the constants. Remember, in this model we haven't added the constant. I commented that out. And then I could potentially try a different linear model on a different library, but it's probably unlikely to be very useful. It'd probably be more useful just sticking with this linear model and then playing around with the with some of the processing, like the constant, the transformation, and all that. Now that the linear model has been done, then I'd probably do a different model, different regression model to see if that does better. But that's for another video. So this is linear regression. Any questions, feel free to ask. Any comments, any statements, feel free to state. I appreciate any feedback. Thanks for watching.